Hi everybody! In this video I'm going to teach you about geometric series. So let's think back to what a geometric sequence is very quickly. A geometric sequence is when you can build a pattern of numbers by having a common ratio, which means you are either multiplying or dividing to grow the sequence. So a series is just when you take a sequence and you find its sum. So a geometric series is the sum of a geometric sequence. And of course, everything has a formula. So here, jot this down carefully. The formula to find the geometric series, to find the sum of the geometric sequence, is the sum to the subscript n, which is the number of terms in the sequence, equals one big long division bar, the first term, a sub 1, which is the first term of the sequence, times 1 minus r to the power of n. R is that common ratio we practiced with geometric sequences, all over 1 minus r. So please write that down carefully, okay? Let's do some practice here. Here's my first sequence or my first series, and I want to find the sum of the first 14 terms. Now, I do not want to write out 14 terms of this series. That'd be too much. So let's use our formula. In our formula, here's what we need. We need to know what n is, because we'll be plugging that in. Well, my n is 14, because I want to find 14 terms, the sum of 14 terms. I need to know what a sub 1 is, which is the first term. Looks like that's 4. And then here's the part that we've practiced before. I need to know what the common ratio is. So let's go over here to our pattern and figure out what are we multiplying or dividing by within each iteration. So 4 times 5 makes 20. 20 times 5 makes 21. 20 times 5 makes 100, and 100 times 5 makes 500, so that makes our common ratio 5. So let's put everything into the right position on the formula. The sum of this series through 14 terms is equal to the first term of 4 times 1 minus the common ratio, which is 5, to the power of 14, all divided by 1 minus 5. Pretty awesome formula. Now, I have no idea what 5 to the 14th is, so you're really going to be good at using Desmos by the time you're finished here. So I'm going to go on over to Desmos. Okay. I'm going to start with a fraction bar so that I can make sure this looks exactly like what's in the my input here. And in the numerator, I have 4 parentheses. Make sure you get your parentheses in the right spot. 1 minus 5 to the power of 14. So you need this a to the power of b feature here to write in any exponent you want, and you want 14 there, all over 1 minus 5. Whew, okay. What you're looking at is scientific notation. So let's talk about that real quick. I'm going to write this down. This is saying take the decimal and move it 9 places to the right. So take this decimal and move it 9 places to the right. So I'm going to write down my final answer. That decimal would end up 1, 2, 3, 4, 5, 6, 7, 8, 9. It would end up behind the 4. Let me switch screens here. Here is my final answer. All right, guys, I know that's a massive number, but really think about what you're doing there. You're finding the sum of a geometric series, and geometric series grow really, really fast. Here we're multiplying by 5 each time. We are finding the sum of 14 terms, so it's going to grow quickly. You're going to want a calculator helper here. Okay, let's try number 2. Let's write down everything we're looking for. It says find the first 20 terms, so my n value is going to be 20. The first value in this series is 81, so the a sub 1 is 81. And now let's look at the series to figure out what our common ratio is. What is happening from 81 to 27, or 27 to 9, or 9 to 3? Well, each iteration we are dividing by 3. Divide by 3, divide by 3. So remember back to geometric series, that doesn't mean our R value is 3. It means our R value is 1/3. Each term is 1/3 the size of the previous term. So let's put everything in. I'm finding the sum of 20 terms. The first term in the series is 81. That would be 1 minus 1/3 to the power of 20 all over 1 minus 1/3. Okay. I'll go slow, but I'm going to go over to Desmos and get this typed in. I'm going to hit the divide button first so that I have a fraction bar to work with. I'm putting parentheses everywhere I can to make sure everything stays organized. I put it around my 1/3 so that I can write my exponent outside very clearly. I may have a few more parentheses than I actually need, but I know that I'm keeping everything nice and neat. And there's my final answer. The sum of the first 20 terms is 121.5. This one's much smaller because the values in my series are getting smaller and smaller and smaller over time. All right, let's see what's next here. Wow, they've given us a series and it's completed at 6,144. Okay, so that is the last value in the series. It's not that there are 6,144 terms. That is the last value in the series. So in my S sub n spot, the 6,144 is S sub n. So we don't really know how many values are in here. We don't know what the n value is right now. That's questionable. So we're going to have to do a little bit of work here to figure out the n value. So we might need to go back to what we learned about geometric series so that we could solve for the n value. So 6,144 is the final term of the sequence. The first term in this sequence is 3. Let's see what my ratio is here. To get from 3 to 6, I multiply by 2. To get from 6 to 12, I multiply by 2. So my R value is clearly 2. And I don't know what my n value is. That's what I'm trying to solve for. Okay, so I need to do a little bit of arithmetic here to solve. I'm going to divide by 3 first. 6,144 divided by 3 is 2,048. Okay. To get rid of this base 2, we need a log of base 2. A log is the inverse of an exponent. So I'm going to apply a log base 2 to both sides, and that would cancel out this base 2. Now, I don't expect anybody to know what log base 2 of 2048 is, so that's another good time to use your Desmos calculator. Okay, right here in the functions, under miscellaneous, right down here, log base A lets you choose the base you're going to use. I'm going to use log base 2 of 2048. And I get 11 as log base 2 of 2048. So So log base 2 of 2048 is 11, and now I can finish solving for n. I get 12 as my n value. So now I can go back to the series. Now I'm going to use this formula. The 12 terms in this series add up to 3 as the first term of the series, 1 minus my r value of 2. Now I know my n value is 12 all over 1 minus 2. So I'm headed back to Desmos to finish this out. Get a new problem here. Okay. Start with a division. 1 minus 2 to the power of 12 all over 1 minus 2. I can find my final summation is 12,285. Now guys, I think the trickiest part of this problem for sure is solving for n, especially this logarithm right here. If you need any help with that part, come see me. I'll be happy to help you work out how to solve for n. Okay, let's keep going down the page here. Let's start talking about this summation notation. We like this summation notation. It works really well for arithmetic and geometric series, and if you're really confident in your skills on Desmos, it's a breeze. I do want to show you how to use the formula, so let's look at that. Remember, in this formula, I'll write it down here so I don't have to keep moving the screen back and forth. In our series, for geometric series formula, the things we need are the first term. Okay, so to get the first term, I could just plug in a 1, so 2 and then 1 minus 1. Well, 1 minus 1 is 0, and anything to the power of 0 is 1. My r value is 2, so every term in the sequence is multiplied by 2. Okay, and I'm working to a sum of 25, so my n value is 25. So if I want to plug this into the formula, here's what it would look like. The sum of the first 25 terms, the first term is 1, the r common ratio is 2, n value is 25, all over 1 minus 2. And then I got to take that to Desmos and plug everything in. So I'm going to have to use Desmos either way, or some kind of calculator. I keep saying Desmos because that's our state-approved calculator. I'm very thankful it does that work for me, because look at this, 33 million so-and-so. It's really good to have a calculator that can handle these kind of numbers. Some of the classroom calculators I've seen can't handle that kind of load. So Desmos is a great choice here, okay? Okay, don't forget, you can do this entire problem using summation notation. It's wonderful. It's such a nice tool to have. So that summation notation is in the functions feature on the miscellaneous tab at the bottom. This was an n value from 1 up to 25. And the function is 2 to the power of n minus 1. I have to put another set of parentheses to keep that in the exponent, n minus 1. So you can get that both ways. If you look here at my screen, you can see where I used the summation formula, and then I also used the sigma notation. So you pick what's best for you. I'm going to assume most students are going to use the sigma notation. It's just so quick. In fact, we're going to work number 7 together only using sigma notation. All right, so in number 7, check out the values here. K starts at 6 and ends at 20. So when you're plugging in those values, make sure you're being careful. Not everything starts at 1, and that's really when sigma is handy. Sigma function. Our variable this time is K, so you might want to swap that out. Just be consistent all the way across. If you're using K in the on the bottom of sigma here, you have to use K in the formula and vice versa. I got -4 times -3. Now, when you put in this exponent, guys, if there's multiple things in the exponent, you may have to put it in a set of parentheses just to tell Desmos everything is up there in the exponent. Ooh, man, we're getting this scientific notation again. So just to reiterate what scientific notation is saying, it's saying take this value and move the decimal 9 places to the right. It is 9 times bigger, or 10 to the 9th times bigger. So 1, 2, 3, 4, 5, 6, 7, 8, 9. The decimal would be at the very end. So we would have, golly, a huge number. And we may want to write down, make sure you're writing down that you're doing that on Desmos so that you know how you handled that problem, okay? Okay, I'm going to stop this video here. The next video is for the back of the notes about an infinite geometric series, but take a break. Try the even problems that we haven't done. I'll put the answers right here so you could pause your screen and then have the final answers right here on the screen. Or, of course, you can just check the answer key. But see what you can do about these even problems before moving forward. Okay, happy studying.